Good morning, everybody. So today's speaker is Martin Hankey, who is visiting us here. That's great. So in fact, he got his diploma and his PhD here at ETH in this very lab. But then he moved on to bigger things. He has for many years he has been a professor at the University of Notre Dame in Indiana, both at the electric engineering department and in maths and statistics. And he's one of the world's top experts in stochastic modeling analysis of wireless networks and other things. I won't repeat everything that his CV it has been an announcement. You have seen it. So I will give the floor to Martin. Please, I think I would say, because it's recorded, turn off not only your audio, but also your video through the talk. Maybe it's a bit on the recording, maybe awkward. Okay, Martin, you have the floor. Great to have you.
Thank you very much, Andy, for the introduction and for hosting me and my wife on our sabbatical. Yeah, it's great to be back after some 20 plus years now at EASY and ETH. So today I'd like to share some of our views on wireless networks now, and in particular focus on this, what we call utopia of peak performance. So the talk is centered around three themes. Now, first, I will present our view on wireless networks and their current evolution. And then I'll introduce stochastic geometry as a key tool for modeling, analysis, and design. And lastly, I will discuss the concept of meta distributions that we've developed, actually started on our last sabbatical some 7 years ago. And we'll see that this intersection here in the center is actually quite powerful to address some of the key issues as we see them in wireless. So this is the standard plot that we usually see now when people give talks about wireless networks. Now they will first show this nice exponential increase in the peak data rates that we have been witnessing over the generations of the cellular networks from 2G, 3G, 4G, now 5G. So yeah, a lot of effort has been put in, and we are in the order of gigabits or tens of gigabits nowadays. And for 6G, people are talking about terabits. So instead, what I would like to focus on is a curve that actually points downhill instead. And this is the ratio between this peak rate and the actual rate that the user experiences now in the real world. So in 2G, everything was essentially circuit switched. So we would get maybe only 10 kilobits per second, but we would get most of that most of the time. And this ratio has been steadily decreasing again, exponentially. And now this red dot down here is what is currently proposed, or what people want to achieve for 5G. So that is slightly less than 1%. That's the ratio between the so-called user experienced, between the peak rate and the so-called user experienced rate, which is defined as the performance of the 5th percentile user. So if we order all the users according to their performance, so that's the maximum rate of the bottom of the 5% of users, no, or the minimum that 95% of the users achieve. So that's the user experience data rate in 5G parlance. No, and if we extrapolate a bit, then maybe that goes even further down for 6G. So there is this widening gap between what is advertised by the cell phone manufacturers and operators and the performance that is actually experienced. We see that there is an increasing uncertainty. We are less and less sure now how close to the peak rates we might actually get. And it turns out now that it's almost impossible to get anywhere close to peak rates. So the question is, how can we analyze percentile performance and improve it. And then in fine print, even maybe encourage operators to advertise and publish actual or experienced performance instead of just the peak rates. So let's look at a couple of analogies. Now, to me, it is surprising that most users, they tend to just accept data rate promises now and say, oh, this device and this network gives you up to 2 gigabits per second or up to 10 gigabits per second. So we tend to accept that and not ask, okay, but what do I actually get? No, so if we compare that with the situation at the job interview, where at some point you might ask, okay, what's my salary going to be? And then the answer is, oh, the peak salary at our company is $10 million per year. No, clearly we wouldn't be satisfied with an answer like that. No, even though there is, of course, the smallest chance that eventually will become CEO and make that amount of money. Or if you go and buy an electric car and you're told that, oh, this vehicle has a peak range of 10 megameters per charge, which again, now there is the slimmest chance we might actually get that far. If we drive downhill for 5,000 kilometers and then we have strong tailwind for another 4,500 kilometers, and then we drive normally for 500 kilometers, we might actually get there. Now, I found only one other industry where these up to statements are actually acceptable. Now, and these are the lotteries, now where we know most people are aware that on average they're going to lose money, but they say, oh, the peak win now that I could get might be $100 million. So we play the lottery. No, but generally, when we are purchasing a cell phone, we want to acquire a communication device and not a lottery ticket. So let's talk about interference. Now is one of the key issues. So at the wireless receiver, now we have usually noise, but we also have power from undesired signals that in most cases we cannot really do anything useful with. So we treat it as noise. And this is nowadays now the key performance limiting factor in most wireless systems. Now certainly cellular, but also increasingly in Wi-Fi. And the quantity that determines the performance in terms of throughput rate, delay, reliability of a link is this signal to interference plus noise ratio, SINR, where we have the signal power in the numerator and then the interference plus noise power in the denominator. And if interference is much larger than the noise, which is often the case, we can ignore this the noise term W, and we could just focus on SIR, signal to interference ratio. Now, the problem is with the peak rates that were advertised is they assume that there is absolutely no interference. So they're essentially based on the assumption that we are the only user in the world. And on top of that, we have really great conditions and are very close to base stations and so on. So as a consequence, now if interference limits the performance, then users can really only achieve rates that are much smaller than the peak rates. One more analogy, a local one. Now, somebody might tell you that driving in Zurich is extremely efficient because you can cross the entire city in only 12 minutes. Now, if we do the simple calculation now that people do when they calculate peak rates, then we say, okay, we have a speed limit of 50 kilometers per hour. And that means, we can drive 53 without problem. So 10.6 kilometers and 53 kilometers per hour, that's exactly 12 minutes. So that will be advertised. But of course, now everybody who's driving knows that this calculation ignores interference. Here, in terms of other cars, traffic lights, stop signs, pedestrians, trams, construction, and COVID demonstrations. So it's going to take much longer, and we'll never get from Wollishofen to Seebach, say, in 12 minutes. So here is a picture of a generic wireless network, where we focus on a receiver R here in blue that attempts to receive a message from a transmitter T at a certain distance in the presence of other transmitters that might be active or inactive at the given time. And we see some of the other distances here shown also. So what is important is that these transceivers, they are embedded in space. Now, often we model them as points on the plane, or maybe if we talk about underwater or UAVs, we might use a three-dimensional space. Now, this interference, now that is the key here, is a function of all the distances and the propagation conditions. And most of them are unknown now at the receiver, now under consideration here in the middle. So here's the high-level view of what wireless is. Now, wireless is at this intersection of space and uncertainty. Now, so these are the two big things now that we need to be managing and dealing with. Space matters because concurrent transmissions that happen on the same frequency, they need to be separated in space. Now, that's very fundamental. As a result, space is really the critical resource, and wireless networking is about managing space and uncertainty. Of course, you would argue that, oh, but the spectrum, no bandwidth and time is as critical, but these are much easier to handle and much better understood, no? Because with time, we know we can turn on and off very quickly. We have very good control over timing. And with spectrum, now we can build or design very good filters. And all of that is under our control, whereas with space, we don't really have exact control, know how signals propagate and attenuate over space. So that is a much more difficult problem. So if you think all the issues that arise in the design of wireless networks and all the great techniques that people have come up with, they are really all about space management, uncertainty management, or both. No, so cell phone providers, they're worried about placing their base stations. Now they're worried about how to associate users with base station, power control, small cells, densification, feedback, now multiple antenna systems, base station cooperation, interference cancellation, carrier sensing, non-orthogonal multiple access, intelligent reflecting services, any kind of diversity scheme, edge computing, caching. These are all fundamentally spatial ideas, ideas for space management or reducing and managing uncertainty. So how do we deal with uncertainty if we want to do analysis now, as opposed to, say, run simulations? So we're dealing with uncertainty, we use stochastic modeling. Now, so that is the first arrow here pointing down on the left. And secondly, how do we deal with space? Space is about geometry. Now we combine stochastic with geometry. Now we get to this tool, stochastic geometry. So this tool provides us with both the models and the tools for wireless network analysis. And in particular, now it gives us an analytical handle on this interference here in the middle, which is really the elephant in the room, so to speak. Now, you might have heard in recent weeks, this big elephant has been in between the airline industry and the cellular industry in the US now in the discussion whether it's safe to operate 5G networks in the vicinity of airports because they might interfere with the altimeters that the airplanes are using. So stochastic geometry is really the only theory that permits a characterization of the interference. So let's talk a little bit about modeling. So what do we model as random in general? So there are two things mainly that we want to model randomly. First is everything that is very hard to compute. So these are things that are deterministic but difficult. So in wireless, this is, for instance, the multipath propagation of wireless signals, now also known as small-scale fading. So the constructive and destructive superposition of the wireless signals that travel along different paths and get reflected and scattered and refracted and so on. So you can also think about throwing a dice. Now, if I throw a die or multiple dice, there's nothing inherently random about it, but we would still model the outcome as that of a random experiment because it's very hard, to calculate on which side the die is going to land. Secondly, we want to model as random what we cannot possibly know. No, in our case, what cannot possibly be known at the transmitter or receiver under consideration. So these are distances and the channel states to the interfering transmitters now, most importantly. So the standard model for the received signal strength over the wireless link now is signal power S is a product of the transmit power P, some random variable H that we use to model the channel state or fading. And then we have a link distance R, of course that could be a random as well, and then a path loss exponent alpha that is usually assumed known and deterministic. Now, we use a so-called point process to model the transceiver location, because we want to, again, model these as random for the reasons given above. So this is a random set phi here, whose elements now we may denote as x1, x2, and so on. So this is a discrete subset on the plane. And with that, we can express the signal interference ratio now as this ratio with the transmit power of the desired transmitter, its channel state, the distance raised to the power minus alpha. In the denominator, we have the powers from all the other transmitters that we are not interested in. So these are the interferers. So if we look at this SAR expression, now we have random elements. Now these are the fading, so H0, Hx. These are usually and reasonably assumed independent, identically distributed, but they vary over time. Now, even if we have micromobility, we move just a little bit or something in our neighborhood moves. Now, these are terms that are going to vary over time. And then we have this point process of locations. So this is spatial and in most cases assumes static, because for the duration of a transmission, these transceiver locations are not going to change. And usually, now when we operate a wireless link, now we want the receiver and possibly the transmitter to learn the channel state, which is the product of the small scale fading term and the distance. But we cannot expect that we can learn anything about the entire point process of locations or their fading state. So this point process phi, this is the central object in stochastic geometry. So we can view this as a random set or a random counting measure a bit more generally, whereby phi of b, we denote the number of points that fall into a set B, into a subset of the plane. So the most prominent example that probably is used in 95% of the literature is the Poisson point process, where the number of points falling in set B is Poisson, with a mean that is proportional to the area of the set, with the proportionality constant lambda, which is the density. And furthermore, if we look at two disjoint sets, B1 and B2, the number of points are independent. So this is just a natural higher dimensional extension of the Poisson process that we see in an introductory probability course, that is a Poisson process on the real axis or on the time axis. So this offers us two key advantages, such spatial modeling. First, it offers us tractability, because if instead of using this random point process model, we were to assume that the locations of all interferers were given deterministically, we would get very unwieldy expressions. We would just have a huge sum, with distances and powers and so on. So it would be very hard. And secondly, we would lose all generality because the result would be specific to that particular realization of the network. Now, so by averaging over this point process, we can obtain results that capture the likely network configurations now, and we get a nice average elegant result. Now, we can compare this with fading models. Now, if we take a popular fading model like Rayleigh fading, no, certainly this has had the same advantages. No, it has proven to be really tractable, and it gives us generality because it averages over many different possible fading states, as opposed to, say, having to run complicated ray tracing algorithms. So this is the point process is really the spatial counterpart of a fading model that we've been using for decades. So let's look at an example of what stochastic geometry can do. So this is kind of a basic model for a cellular network. So the blue points here are the locations of the base stations. And here we assume that they form such a Poisson process. And we are using the entire bandwidth in each cell. Each user is going to be served by the base station to which it is closest. So if we focus on this cell in the middle here, in the green cell, a user that is residing in this cell is going to be served by its own base station here, and everybody else around acts as an interferer. So we have an SIR, that is the ratio of the good power, the green power, and the red power, which is the interference from everybody else. Now, if we walk through this network here, then the SIR shown on the right is going to fluctuate. Here we assume first that there's no fading. So this is just a matter of distances or relative distances. Now we see as we approach the cell edges here, these are the red zones, the SIR is going to drop below 1 or below 0 dB. Conversely, if we get very close to a base station, now we get these nice peaks in the SIR. So these are the fluctuations now when we walk around a city that our cell phone is going to detect. And then if we add fading on top, then of course we have more spatially rapid fluctuations, which are the purple curves here. And now a basic question that we might have is, okay, so what if we walk around, what fraction of time are we actually above a certain threshold here, say 0 dB? Instead of walking around, now we can just say, okay, what fraction of the entire space, of the entire plane achieves an SIR larger than 0 dB? And now, because this model, now the Poisson process, is ergodic, we can exchange the ensemble average and the spatial average. So the fraction of the curve that is above a certain threshold corresponds to the ensemble average. In this case, we use a complementary cumulative distribution of the SIR. So this expression here, the F bar, now that's the probability that the SIR exceeds theta. That is the area fraction that achieves a SIR higher than a given threshold. Now, assuming now that code words are reasonably long, then we can equate this SIR CCDF with the success probability or reliability of a transmission, and theta represents the modulation and coding rate together. So then this makes sense. And even if we have very short messages, now then we just focus on calling this the SIR distribution. Now let's make things a bit more interesting and consider a multi-tier model. Now nowadays, cellular architectures are heterogeneous. So we have macro base stations. These are the blue crosses. They transmit at higher power. We have micro base stations, so the red circles here. And then people might have femtocells in their homes. These are the little green ones. And then we see that the user might be associated with a macro base station if it is not in the vicinity of a micro base station or a femtocell, and so on. Now, so we can be served by different layers in this heterogeneous architecture. Now, more abstractly, we can model this as a superposition of several independent Poisson processes. Now, so here, say we have this three-tier model. The blue ones are the big ones. They transmit at high power. Here they have density 1. The red ones have density 2, and the green ones have density 3. And we can express the SAR in the same way. We assume that each user, again, is served by the base station that provides the highest power. No longer the one that is necessarily closest, but the one that gives the highest power. So we focus on a user at the origin. Now each, in this model, everything is stationary. Now, so each location is the same. We could pick any deterministic location. Now, when we average over this base station processes, this user becomes what's called the typical user. So that is a user that behaves in some way now like the average user. We assume that the fading is Rayleigh, which means these random variables h are IID exponential with mean 1. Now, what we can show with stochastic geometry, without too much effort, we can show that the SAR distribution at this typical user does not depend on the number of tiers. It does not depend on their densities, and it does not depend on their transmit power levels. It is simply given by this expression here, where the 2f1 is the Gauss hypergeometric function, which is now standard in most numerical packages, Maple and Mathematica and MATLAB, and so on. So this parameter delta here is just a mapped version of the path loss exponent that makes the expressions a little nicer. If we specialize the path loss exponent to 4, then we get a really remarkably simple expression. Then we get this 1/1 square root theta arc tangent square root theta. Now, so this is really as simple as we could expect it to get. So this tells us now it doesn't matter how dense the network is, how many tiers we put, if base stations transmit at milliwatts or microwatts or megawatts, so this SAR distribution is always going to be the same. That's a nice result. Now, that would be very hard to show using simulation, because of course with simulation we can only ever hope to show what's happening in a particular space, in a particular set of the parameter space, and we will never see such an elegant result here. Now, this is the closed form result in the Poisson case, and if we look at other point processes, say lattices, we can approximate this distribution quite accurately by just scaling the parameter theta by a factor g here. So g is 1 in the Poisson case. In a square lattice, g is about 2. Now, so we can say, okay, the square lattice gives us 3 dB gain. Now, if we shift the SAR curves in dB, that would be a 3 dB gain relative to the Poisson process. But it's not, they're not that far. So this SAR distribution now can be interpreted in two ways. Now, one is this ensemble average. So we pick any location X. If we take an average over the fading and the point process, now that is the expected indicator that the SAR at X exceeds theta. And secondly, it is the spatial average of the area fraction in which the SAR exceeds theta in any realization of the point process. Now, and this is important now because, of course, in practice, now the base stations, they are put in a certain way and they don't move around. Now, so the ensemble averaging doesn't really happen in the real world, but the spatial averaging certainly does. Now, if we walk around or we want to figure out what the user population as a whole is going to see, now then we are actually looking at this spatial average here given by this integral. Now it's just an average over an increasingly large disk here centered at 0. Now, we need to keep in mind that the locations for which the SAR exceeds theta, they are changing quickly over time because the fading is going to change. Now, so this condition, SAR larger theta, is not really suitable now to talk about network coverage, because then we would have to say, okay, now for 10 milliseconds we are covered, and then for the next 20 milliseconds we're not covered, and so on. Now, so coverage should really be about space only and not about time. Now, so that's a really nice result now in this SAR distribution, but it really has this severe limitation that it does not reveal any information about the disparity between different users. Now, so we cannot use it to access any information about the user percentiles, which we would like to do. And if we look at it carefully, although it kind of looks like a distribution, it is the SAR distribution, it is really just an average, and it models the two key random elements in the network, namely temporal and spatial randomness. So if we look at individual users for a moment, now, so we have another network here with base stations in red, and the users in this case form a lattice. These are the blue guys here. And assume we want to transmit at a certain given rate corresponding to a SAR threshold theta of 1. And each user transmits or receives from the base station, now focus on downlink, 1,000 packets, and we want to know what is the fraction that the user receives. And then we arrive at these little numbers here. These are the percentages or the per user reliabilities. Now, so mathematically what we're doing is we are conditioning on the point process. We are holding everything fixed spatially, and then we're just averaging over the fading. And we have individual numbers, and we see that users that are further away from their base stations, they're going to have a lower number. Now there's one in the middle that is 0.06, only has 6% reliability. And those users that are very close to base stations, they get up to 98%, or one has even 100% here on the left. So what we have calculated before is actually the spatial average over all these black numbers. So if we denote the individual reliabilities as this capital PS, then the SAR distribution at SAR threshold 1 is the expectation here, which is 56%. So that's just the average, but if we want to determine percentile performance, now we actually need to know the distribution of these black numbers and not just their average. So let's look at these reliabilities in a histogram. Now, so on the left, we have case 1, and we take the reliabilities now of a large number of users, and we show them here in this histogram, now, which is now an empirical PDF. We might have a distribution like this, now where we have some concentration near 1, but everything is spread out. On the right, in case 2, we have a totally different kind of a distribution. Now, where we don't have very small reliabilities, we don't have very high ones. Now, everything is more concentrated. Now, in both these cases, the average is 0.7. So we have 70% reliability. But looking at this, it's clear that case 2 is much more desirable for the user and the operator. Now, because we don't really have users that are in really bad shape. But the standard analysis, now that is mostly used, makes no difference between the two, because the only thing it gives us is really just, oh, it's 70% on average. So now if we want to know what fraction of users achieve a reliability of X at the given rate of transmission, then we have in case 1, we have a curve like this. So now this is the complementary cumulative distribution. In case 2, it looks like this on the right. And now we can invert this and obtain the 5 percentile reliability. So we draw a line at 0.95, we get this point here. So on the left, we have 21% reliability. On the right, we have 58% reliability. So we see that the 5th percentile performance now gives us much better information about the network performance. And we can also observe that techniques now that have been proposed that boost the mean performance can actually be harmful to the 5th percentile user. Now, so there are techniques that whose effect is just that the rich are getting richer, but then the poor are getting poorer, now, and things are getting worse in terms of the user disparity. And there are other techniques, maybe better ones, that have little effect on the mean, but increase the concentration on or fairness between the users. So how do we analyze the distribution instead of just the mean? Now, so this is where this concept of meta distribution comes in. So generally, just take a function now from R2 to R and a couple of random variables, X and Y. And then we apply this function f to X and Y, and we call the result C here on the left. Then certainly we can calculate the mean. So that's the expected value of C. And then if we want to know more, now we add an indicator function and we add a little parameter, a dummy variable Z, and we arrive at the complementary cumulative distribution. So the expected value of the indicator that the big Z exceeds the little z that we have on the left. But now this distribution does not reveal anything about X and Y or how Z depends on X and Y. So in order to do that, we add another expectation over X only. We add another dummy parameter, little x, and we get this meta distribution here. So we first take an expectation only over X of the indicator that C exceeds C. That gives us a conditional distribution. And then we are taking that number between 0 and 1, we compare it against the second parameter, little x, and take the expectation over it. So that's what we call the meta distribution. And then going back up, we can integrate over X, we get the standard distribution back. We can integrate over Z and we get the mean back. Now on the right, now if we just declare a new random variable U, that is the conditional distribution of Z given Y, we realize, now as I said before, that the standard distribution is just a mean, whereas the meta distribution is in fact the distribution of that random variable U. So in summary, this meta distribution is a distribution of a conditional distribution, and it shows how X and Y individually affect the random variable Z. So we can write this probabilistically here. So that's F bar now of Z given Y first with the two parameters, this probability. Yeah, we can write it in these two forms. So let's do a little toy example. Now, if we have two independent exponential random variables with mean 1 and mean 1 over mu, and the function f we are looking at is just a ratio. So we define z to be the ratio x divided by y. Then it's easy to calculate the distribution of z. That's mu over z plus mu, and we know the mean does not exist. So now we introduce this new random variable u. That's the conditional distribution. That is e to the minus yz. And from that, we can calculate the meta distribution. So that's the two-parameter distribution here on the right in the first equation. And as promised, of course, we can retrieve the standard distribution of z by integrating over x. And then instead of first conditioning on y, of course, we can also condition on x first. So that's what I call the dual meta distribution. It looks like this. And in many cases, it just turns out to be the inverse of the first one. Now, so we can establish the conditional for which these are just inverses in X, these two. So that's a toy example. Now let's look at the toy application. If we look at the cellular uplink and we focus on the signal power received at the base station, that again form a Poisson process of given intensity lambda. If users are served by the nearest base station, then the distance, the link distances are Rayleigh distributed, now with the given mean here, 1/2 square root lambda. If signal propagation is free space, we have a path loss exponent of 2, and the signal power received is just h divided by r squared, where due to Rayleigh fading, h is exponential. Now, this is a simple enough example that, again, now we can do the calculation and we arrive at the meta distribution here. So where what we are interested in is the signal power S. What we are conditioning on first is the point process phi. So that's what we keep static. And then we get this meta distribution. So the blue curves in the plot here show the fraction of users that achieve a signal power larger than C with probability at least X in each realization of the point process. So for the curve C equal to 1, there is a little circle here that marks a spot. So that spot shows that 80% of the users achieve a signal power of 1 with probability at least 0.6, 60%. So here, using the meta distribution, we have achieved a clean separation of temporal and spatial randomness. So we let the temporal randomness go because we have short-term fluctuations. We hold on to the spatial randomness. And then we get the separation that gives us these user percentiles. Now, in the downlink case, if we only consider the nearest interfering base station, again, we get the closed form result. So that's the first expression here. Again, that's a little exercise, simple. On the other hand, if we consider all interferers, as we would have in the real world, then a closed form solution does not exist. But what we can do, we can calculate the moments of the conditional distribution. Now, so if this random variable u, again, is the conditional distribution of the SIR given the point process, we can calculate moments of u. Now, it's just the nature of the tools we have from stochastic geometry give us access to these moments here, which in this case is actually very simple. Now, previously we had a 1 here in the hypergeometric function, and now we have a b here. So that's the only change. So for any complex number b, we can get this b's moment by just plugging in a b here instead of 1. And then the question is if we can retrieve the distribution from the moments. Of course, that is an old problem, and people often propose to use this inversion, due to Gill and Pelaez, where if we have imaginary moments, we can calculate the meta distribution using this integral. However, this turns out to be tricky to evaluate, because we have an infinite range here, and we need imaginary moments. And there's not a single case known for which this Gill-Pelaez integral actually has a closed form solution. Now, if we know all the integer moments, now this problem is known as the Hausdorff moment problem. But in practice, we only can calculate a finite number of moments. So that's a truncated problem, which has infinitely many solutions now in most cases. We can calculate the infima and suprema over these distributions now with some effort, but actually efficiently getting good approximations is ongoing research now that we are currently pursuing. Now, a natural approximation is to use a beta distribution where we match first and second moments, and that often gives decent results, but of course there are no guarantees here, now how close we are to the exact curves. We can also just look at the variance. Now that gives us some basic information on how concentrated the per user performance is. Here is an example now of this two-parameter distribution. If we take this Poisson process with Rayleigh fading, a pass loss exponent of 4, we get this landscape here that shows us the fraction of users who achieve an SIR of zeta with probability at least x. Now, there's a little point here that is marked with a triangle, and that is an interesting point because here this is the point after which, if we further increase zeta, then the distribution here becomes infinitely steep. That means if we just increase the reliability a tiny bit from 0, we get a drastic reduction in the fraction of users that achieve that reliability. Now, these meta distributions give us access to interesting trade-offs. Now, if we look at contours in the meta distribution, the contours reveal the pairs of zeta and x that a given fraction of users achieve. So if we map zeta to the rate using this, what I call optimistic mapping, log 2 of 1 plus zeta inspired by Shannon, we can plot a rate reliability trade-off. So we have this spectral efficiency or normalized rate on the x-axis. We have the reliability on the y-axis. And we can plot the performance of the median user, the 50 percentile user. That's the magenta curve here. And we also can plot the 5th percentile user. That's the blue curve. Now, and we see how the blue curve's trade-off is significantly worse than the 50th percentile user trade-off. And one goal would be, now we could try and narrow the gap between the 5th percentile and the 50th percentile user here. So what kind of insights can we get? For instance, we can show that densification has little effect on the SIR, not just the SIR distribution, but the entire SIR meta distribution. So we put in a lot more base stations, we get more interference, we get more signal power, and the net effect is 0. But of course, it helps with the capacity because each base station is going to have to serve fewer users. If we look at power control in the uplink, which is very common, now every cellular network uses that, we see that it barely affects the SIR distribution in terms of the average, but it drastically improves the 5th percentile performance. Now, so it actually achieves a good user concentration or improves the fairness in the network. If we look at base station cooperation, where the users combine signals from multiple base stations, we observe that this certainly improves the average, but it also widens the gap to the 5th percentile user. Now, this is actually a case where the rich get richer. Instead, now the way we should use coordinated multipoint, now this base station cooperation, we should use it only for users that are near the cell edges. Now we should make it location specific. Non-orthogonal multiple access, NOMA, now has been popular, hasn't quite made it in the 5G standard, should be restricted to users close to base stations, even though without interference, now the logic would dictate that the channel disparity between the two users that are jointly served should be big. Now, but this doesn't work in the cellular case with interference. Now, previously, we talked about this reliability-based framework, and that is quite useful for shorter messages, low latency, where we have limited diversity. Conversely, when we have longer messages or code words, or we have huge bandwidth, many antennas, hybrid ARQ, now we might want to use an ergodic point of view, where inherently, the transmission technique in itself averages over fading, and the rate is chosen such that outages do not occur. Now we're essentially adjusting the rate to the channel. Now, if we normalize this resulting rate by the bandwidth, now that's what we call ergodic spectral efficiency, which we measure in bits per second per hertz. Now, sometimes we see that, again, inspired by Shannon, people are trying to evaluate an expectation of log2 1 plus SIR. When we plug in the SIR expression, now we get this expanded form here on the top right. Now, again, as we have said before, this is an average that just lumps together everything. All the randomness is together. There is also an underlying assumption of Gaussianity, now, which is reasonable, let's say in this case. But most importantly, this expression assumes that the receiver knows all the fading coefficients, h, all the distances, and actually gifting the receiver with all that information results in a fairly loose upper bound. So what is a better approach? A better approach is, again, to condition first on the point process and eliminate the fading in the SIR expression. Now, in this case, not using a distribution, but an expectation. So how does this work? We look at the geometric form of the SIR here given by this rho, which is like an SIR, but all the fading is gone. Now, so we just have the spatial locations left. So this one captures the network geometry. And then we take an average over the fading of the desired link. So that's this parameter or function C of rho. So that's the expectation over H. So now we have log2 1 plus H times rho, which means we are putting in the fading in the desired link in the numerator, but we are not putting in any fading in the denominator. So we call this the ergodic spectral efficiency given the point process. In the case of Rayleigh fading, we get an expression here in terms of an exponential integral. Now, it turns out that ignoring the fading in the interference gives us a tight lower bound. And tight lower bounds are, of course, much preferable over loose upper bounds. And once we have this function C of rho, now we can apply stochastic geometry to find its distribution. So this is like a degenerate form of the meta distribution, where the first distribution is not a conditional distribution, but just a step function. So these are some of the results that we can obtain if we want to look at the fraction of users that achieve a certain ergodic spectral efficiency. Now on the left, so we have curves for SISO, now single antenna case, and 2x2 MIMO. And there's a little inlet now where we zoom in. And we can see that with single antenna, now in this case, there's essentially no user that gets less than 0.18 bit per second per hertz. With 2x2 MIMO, everybody gets at least 0.3 bits per second per hertz. Now, so again, we have a full distribution here. And an interesting observation here is on the right. Now, if we plot the logarithm of these ergodic spectral efficiencies, they're almost log normal now, so we can give a simple log normal approximation of their distribution. As we start to conclude, let me just make a remark about proper averaging. Now, so the averaging we'd like to do is over the users, not over time. So let me illustrate that going back to the driving situation through Zurich. Now, if you drive at 3 in the morning from the zoo to Schlierens, it might take you 24 minutes. If you drive at 5 p.m., it might take you 48 minutes. So what's the average of 48 and 24? The average is 47.5. Now, why is that? The reason is that there are 50 times more cars on the street at 5 p.m. than at 3 a.m. So we have to give the 48-minute value 50 times more weight than the 24-minute value. So we are very close to the 48 minutes that it takes us at 5 p.m. Now, it's the same for cellular users. Now, many more users are active during daytime. So nighttime performance is irrelevant now. So we need to focus on the fully loaded conditions where we actually have significant interference. And the same argument holds spatially. Now, if we look at crowds, they tend to have a lot more weight in this average than a few isolated users somewhere. So in conclusion, we contend that advertised or peak rates are utopian. Now, the actual performance is a vanishing fraction. Now that gets smaller and smaller as we go through the cellular generations. If we evaluate averages sensibly, now then of course we get better information, but we still do not know what most users can expect. So we need to focus on percentiles. Space is the critical resource in wireless, to manage interference, which makes stochastic geometry the natural analytical tool. And if we combine it with the concept of meta distribution, it allows the characterization of the complete distribution of the performance metrics for the users. And if we focus on the 5th percentile performance, now instead of averages, let alone peaks, we can engineer wireless networks that behave more deterministically, more predictably for all users. And again, small print, we like to hold operators more accountable for what they advertise. Last word, here is a picture I took a few years ago somewhere in the US. Now, good cell phone service, yeah, you have to go to this next pullout. And if we continue on the current trajectory, this might still be the case now for a while. At this pullout, we might get 5% of the peak rate, which is better than the 5th percentile rate, but of course it's still quite limited. So the goal should be that we can remove these signs and get good performance, not terabits, but good performance everywhere and at any time. Thank you.
Well, thank you so much. That was a wonderful talk, very beautiful and most instructive. So I'm in awe.